A modern skyscraper would collapse without its binding paste, yet ancient civilizations built monuments to last forever without it. They mastered the art of mortarless construction, creating wonders that still stand after thousands of years. By the end of this journey, you will see ancient engineering not as primitive, but as a sophisticated science we are still learning from today. How did they cut 100-ton stones with such precision that not even a blade of grass fits between them? What forgotten knowledge allowed these structures to dance through earthquakes and outlast empires? In a world of temporary things, what does it truly mean to build something permanent? The real puzzle begins not with the finished monument, but with the first stone. Think about how a simple brick wall is built today. You lay down a row of bricks, you spread a layer of mortar between them, and you place the next row on top. That mortar acts as a glue and a cushion, filling in the inevitable gaps left by imperfectly shaped materials. It forgives minor errors. Now take that mortar away. Every single brick, or in this case, every massive stone block, must be shaped with such incredible accuracy that its neighbor fits perfectly along every edge, top, bottom, and side. There is no forgiving paste, no flexible filler. The entire immense weight of the structure, sometimes thousands of tons, is transferred from one stone to the next through nothing but pure, precise contact. This is the heart of mortarless construction, a technique known as ashlar masonry or dry stone building. It is a three-dimensional stone puzzle of unimaginable scale, where every piece is custom carved to bear a specific load in a specific place. The goal was a joint so tight, so seamless, that it became virtually invisible, a line drawn with stone. This pursuit of the perfect fit was not born from a lack of options. These civilizations often had access to simple binding materials like clay or lime. They chose not to use them. Why? Because they understood a fundamental principle of engineering. Mortar over centuries can crack, crumble, and wash away. It becomes the weakest link. By relying solely on geometry and gravity, they built systems where the strength was in the stone itself. Each block, locked in place by its neighbors and the colossal weight above it, creates a structure that can flex and settle without shattering. This is why so many mortarless monuments still stand in regions plagued by earthquakes. They don't resist the Earth's movement, they dance with it, stones shifting minutely before settling back into their immaculate embrace. So when we look at a wall where not even a blade of grass finds purchase, we are not looking at a quaint ancient method. We are looking at a deliberate, advanced engineering solution. It represents a mastery of material, mathematics, and long-term thinking that turns a simple stack of rocks into a conversation with eternity. To witness this principle on its most monumental scale, we must look to the sands of Giza. Here, the Great Pyramid stands not merely as a tomb, but as the ultimate expression of dry stone engineering. Constructed around 2,560 years before the Common Era for the pharaoh Khufu, it is a mountain crafted by human hands from an estimated 2.3 million blocks of limestone. Each block weighs several tons, and the entire structure relies not on glue, but on gravity and geometry. While a small amount of gypsum mortar was found in some inner chambers, the pyramid's core is a mortarless masterpiece. Its strength comes from the colossal weight of each stone, perfectly placed and locked by the stones around it. The builders achieved something almost incomprehensible, leveling a base covering over 13 acres to within a fraction of an inch, and aligning the sides to the cardinal points with astonishing accuracy. The joints between the massive casing stones, now mostly gone, were said to be so precise that not even a hair could be inserted between them. This was not random piling. It was a precise, three-dimensional puzzle executed on a scale that dwarfs imagination. So how did they do it? The absence of cranes or modern machinery has fueled centuries of speculation. One prevailing theory involves water. By wetting the sand in front of wooden sledges, workers could drastically reduce friction, allowing teams to haul these immense blocks across the desert. To lift them, evidence suggests a system of ramps, perhaps spiraling around the pyramid's growing form, turning an impossible vertical climb into a manageable, gradual incline. But the true genius lies in the pyramid's shape itself. Its form is its function. The smooth, sloping sides naturally deflect the punishing desert winds that would erode a vertical face. More importantly, the pyramid is the most stable geometric shape for distributing immense weight. Every ounce of pressure from the stones at the peak is channeled down through the structure and outward into the wide base and the bedrock below. It is a shape that literally pushes down into the earth, settling into stability. This understanding of mass, balance, and the forces of nature allowed it to endure for over 4,500 years. When we see it today, we are not just looking at an old building. We are seeing the physical manifestation of an ancient civilization's conversation with physics, a permanent answer written in stone to a question of timeless ambition. How do you build something that the world cannot forget? But the pursuit of the perfect fit was not confined to the desert. Travel across an ocean and up into the thin air of the Andes Mountains, and you will find a fortress that seems to defy the very concept of gravity. High above the ancient Inca capital of Cusco, the megalithic walls of Sacsayhuamán stand guard. Built in the 15th century, these structures represent a different, yet equally brilliant school of mortarless thought. Where the pyramids are about smooth slopes and perfect symmetry, Sacsayhuamán is about dynamic, muscular power. Its most famous walls are arranged in a zigzag pattern, like the teeth of a colossal stone serpent embedded in the hillside. And the stones themselves are staggering. Imagine limestone boulders, some taller than a two-story building and weighing well over 100 tons, each one a unique, irregular shape. They are not simple rectangles, they are polygonal, possessing multiple angles and sides, some with 12 or more distinct faces, and they are fitted together with a precision that makes the mind reel. This is polygonal masonry, a three-dimensional stone puzzle of unimaginable complexity. The builders did not force standard shapes onto the rock. Instead, they worked with the natural form of each boulder, meticulously carving and adjusting it to interlock perfectly with its neighbors on all sides. The process was one of supreme patience and skill. Using hammerstones made of harder rock, workers would peck away at a boulder, then test its fit against the stones already in place. They would make a tiny adjustment, test again, and repeat, perhaps for weeks or months on a single block, until the joint was so seamless that it became virtually invisible. Why go to such extraordinary lengths? The answer lies in the land itself. Peru sits on one of the most seismically active zones on Earth. A rigid, mortar-bound wall would crack and crumble in a major earthquake. But a wall built like Sacsayhuamán's is alive. During a tremor, these polygonal stones can shift and rock, dancing with the energy of the quake. Then, as the shaking subsides, gravity and their own intricate, interlocking shapes guide them to settle back into their original positions. It is architecture that embraces movement, that understands stability is not about being rigid but about being resilient. This immense effort served a dual purpose. Practically, these were formidable defensive walls, capable of protecting the sacred city below, but their significance ran deeper. Sacsayhuamán was considered a ceremonial house of the sun, a place where the earthly and divine met. The incredible labor, the seamless fusion of stone with stone, was itself an act of reverence. It demonstrated that for the Inca, engineering was not separate from spirituality, it was an expression of it. To build in harmony with the immense forces of the earth was to honor them. So here, in the shadow of the Andes, the stones tell a story not just of defense, but of dialogue, a conversation between human ingenuity and the powerful, living world around it. From the rugged, muscular stones of the Andes, we journey to a hilltop where precision sought not just strength but perfection. The Acropolis in Athens rises from the plain, and upon it sits the Parthenon, a temple of such serene grace it seems to defy its own weight. Built in just 15 years during the 5th century before the Common Era, this monument to the goddess Athena represents a different philosophy entirely. Here, the material was not rough-hewn limestone, but luminous pentelic marble, and the goal was not just endurance, but an ideal of beauty achieved through mathematical harmony. While the Greeks used metal connectors, they were not a substitute for mortar. They were the final, invisible lock for a system that relied first and foremost on the flawless marriage of stone to stone. The builders of the Parthenon were masters of optics and illusion. Look at the columns, they appear perfectly straight and parallel, but this is a carefully crafted deception. Each column swells slightly in the middle, a subtle curve known as intosses, which counteracts the visual effect of a tall, straight line appearing to pinch inward. The columns also lean inward toward the center of the structure, and the entire platform curves upward at its center. These were not errors, they were corrections. The architects understood that to be perceived as perfect by the human eye, the building had to be deliberately imperfect. This philosophy extended to the very joints between the stones. The massive marble blocks were cut with such exactitude that when placed together, their faces met in a contact so complete it created a vacuum seal. Stories tell of builders pouring water over finished joints only to watch it bead and roll away, unable to penetrate the seam. To secure this perfection against earthquakes and time, they employed a hidden reinforcement system. Into channels carved across the faces of adjoining blocks, they poured molten lead around iron clamps, creating a flexible metal bond that held the stones together while allowing for minute movement. Similarly, the columns were not monolithic, they were built from stacked cylindrical drums. A square peg of wood, sealed in lead, was set into the center of the top and bottom of each drum, aligning them with peg and socket precision as they were hoisted into place. This ingenious system allowed for both immense stability and a degree of flexibility. The metal absorbed stress and the wooden pegs allowed for slight settling, all while the exquisite marble geometry carried the load. This was engineering in service of an idea, the pursuit of ideal form. The Parthenon's proportions were governed by the golden ratio, a mathematical relationship found in nature and believed to represent ultimate harmony. Every dimension, from the width between columns to the height of the facade, was part of a single, cohesive equation. The building was a physical manifestation of the Greek belief in a cosmos ordered by rational, beautiful principles. It declared that human reason could perceive and even recreate this divine order in stone. The tragedy and testament of the Parthenon is that, despite being severely damaged by conflict and explosion in the 17th century, its essential skeleton remains. The columns, though battered, still stand in their rows. The entablature, though broken, still traces its lines against the sky. It endures not as a complete temple, but as a profound lesson. It shows us that for these architects, the fit of stone upon stone was never just a technical challenge. It was the fundamental act of bringing an abstract ideal of balance, beauty, and reason into the tangible world. They built a thought, and the thought has outlasted empires. The marble of the Parthenon did not cut itself. The polygonal giants of Sacsayhuamán did not simply fall into place. To create the seamless joints we marvel at today, ancient builders first had to solve a much more fundamental puzzle. How do you shape a mountain? Without diamond-tipped saws or laser guides, they relied on a profound understanding of materials and a staggering degree of patience, turning simple tools into extensions of their will. The process began at the quarry. Workers would locate a suitable stone seam, then use harder stone hammers to painstakingly peck a series of narrow channels around the desired block. Dry wooden wedges were hammered into these channels, then soaked with water. As the wood expanded with tremendous force, it would crack the stone along a clean line, freeing a multi-ton block from the earth's grasp. This raw block was then transported to the building site, a feat of logistics in itself, but arrival was just the beginning. This was when the true artistry, known as stone dressing, commenced. The mason's toolkit was deceptively simple. For the Egyptians working granite, it might be a hammer made of even harder diorite, for others, bronze chisels and wooden mallets. But one of the most crucial tools was sand. By sprinkling abrasive quartz sand between a stone block and a smoother grinding stone, then moving the top stone back and forth, a worker could slowly, meticulously wear down the surface to a perfectly flat plane. It was a process measured in millimeters per hour. To ensure accuracy, they used the ancient world's universal guides, string lines coated in pigment to mark straight edges, wooden frames set at perfect right angles, and simple plumb bobs, a weight on a string, to check for true vertical. But how did they achieve those breathtaking hair-width joints? Evidence points to a brilliant technique often called test fitting or knobbing. Before a stone was considered finished, masons would intentionally leave a few small, rounded protrusions on the face meant to join with its neighbor. They would then hoist the stone into position, a task requiring immense coordination. As the block settled, these knobs would make first contact. Workers would then lower the stone, inspect the points of contact where the knobs had been crushed or marked, and carefully grind those specific areas down. They would repeat this process, lift, lower, inspect, and adjust, sometimes dozens of times, until the two stone faces met across their entire surface. The final descent would be a smooth, silent slide into a perfect embrace. This method required more than just muscle. It demanded a kind of three-dimensional spatial intelligence we can scarcely appreciate. A master mason had to visualize not just the stone in front of him, but the empty space it needed to fill, and the complex shapes of the stones already waiting around it. He was solving a giant weight-bearing puzzle where every piece was unique, and the only solution was absolute precision. This was not construction as we think of it. It was a form of slow sculpture, a dialogue between the craftsman and the rock. Every chip of stone, every hour of grinding was a step toward an invisible goal. A joint so perfect it would disappear, making many stones act as one. The monument's strength was forged in this painstaking, repetitive act of refinement, where the only thing poured between the stones was time and unwavering intention. The final, perfect fit of a stone was a triumph of patience, but it was a triumph that happened at the end of a much longer, more arduous journey. 100-ton block of granite is useless at the bottom of a quarry, and the temple site waits empty on a distant hill. This was the next, and perhaps most visceral, challenge of mortarless construction, moving the unmovable. Without cranes or trucks, ancient engineers turned logistics into a form of applied physics, and communal effort into a powerful social ritual. For the Egyptians, moving the massive limestone blocks for the pyramids likely involved a combination of brute force and brilliant lubrication. Tomb paintings show us a clear image, large wooden sledges piled with stone statues, pulled by lines of workers across the desert. But the secret may have been under their feet. Experiments have shown that wetting the sand in front of such a sledge reduces the pulling force required by half. The water creates a capillary bridge between the sand grains, making the surface firm and smooth, almost like pulling a heavy object over wet concrete instead of loose, dragging grit. This simple act, pouring water onto sand, transformed an impossible haul into a manageable, if still Herculean, task. For the heaviest stones, like the granite used for obelisks and temple columns, they may have built special barges during the Nile's annual flood, using the river itself as a liquid highway to ferry these mountains of stone close to their final destinations. But what about a civilization that had no vast river plains, no dense timber for huge sledges, and lived in a world of vertical slopes? The Inca of the Andes faced this exact reality. They had no wheels suitable for the terrain and no large draft animals like oxen. Their solution was a masterpiece of human coordination and simple mechanics. To move the polygonal giants for Sacsayhuamán, they relied on a symphony of ropes, levers, and ramps. Teams of workers, perhaps hundreds strong, would pull with ropes made from braided leather or plant fibers. To reduce friction, they likely placed the boulder on a bed of logs that acted as rollers, constantly moving the logs from the back to the front as the stone inched forward. For steep inclines, they built temporary earthen ramps, packing soil and stone to create a gradual slope up a mountainside. The process would have been agonizingly slow, a chorus of coordinated shouts, the groan of wood under immense stress, and the minute shifting of stone that marked a day's progress. Some researchers propose an even more ingenious method for certain stones, a technique called stone walking. By carefully rocking a boulder from side to side and inserting pivots or small stones underneath, a skilled team could literally walk a multi-ton block across uneven ground, a delicate, rhythmic dance that turned immense weight into controlled momentum. These were not merely engineering projects, they were social ones. The transportation of a single megalith required the entire community, a shared labor that blurred the line between work and ceremony. The rhythmic pull of ropes, the unified chance to coordinate effort, the collective triumph when a stone finally settled at its site, these acts forged a powerful sense of common purpose. Moving the stone was a physical proof of what the society could achieve together. It transformed abstract loyalty to a king or a god into a tangible, muscular experience. Every person who pulled a rope or placed a log roller could look at the finished, impossible wall and know, I helped build that. The monument's endurance thus became a testament not just to technical skill, but to the enduring strength of human cooperation. The stone's journey from quarry to foundation was where the myth of the monument was born, long before the final, silent piece was set into its perfect, mortarless place. Yet the most delicate operation still lay ahead. The stone, now at the base of the rising monument, had to be lifted into the sky. For the pyramids, this likely meant the construction of colossal ramps, great sloping roadways of packed earth and brick that snaked up the growing structure. As each course of stone was laid, the ramp was extended higher, a temporary mountain built to raise a permanent one. For civilizations like the Greeks, the solution was more mechanical. They developed the polyspaston, an early but effective system of compound pulleys and winches that could multiply human strength, allowing a crew to hoist heavy marble blocks with controlled, deliberate force. The Egyptians may have used a simpler but equally clever tool, a lever and fulcrum system inspired by the shaduf used for drawing water, to pivot and nudge stones into their final positions. Each lift was a moment of supreme tension, a balance of immense weight against human ingenuity, where a single misstep could mean disaster, but placement was only half the battle. The stone had to be placed perfectly, not just in its spot, but within a grand, cosmic order. How do you ensure a structure spanning acres is perfectly level, or that its walls face true north? The builders turned their gaze upward, to align the Great Pyramid's sides with the cardinal points with such breathtaking accuracy. They likely used the unchanging stars, tracking the arc of a single star or the symmetrical shadows cast by a vertical rod. On the ground, they used the world's oldest and most reliable level, water. By digging shallow trenches around the construction site and filling them with water, they created a continuous plane of perfect flatness, a liquid horizon from which all other measurements could be made. Shadow-casting instruments and simple plumb lines gave them true verticals. Then came the final, intimate act of marriage between stone and stone. Using ropes and levers, the massive block was painstakingly lowered onto its waiting neighbors. The masons would listen and watch. Did it seat evenly? Did it rock? Using the method of test fitting, they might lift it again, inspecting the faint dust patterns to see which high points had made contact. With abrasives like sand, they would grind those specific spots down, a process of microscopic refinement. They repeated this cycle: lower, inspect, adjust, until the moment the stone settled with a deep, quiet finality, its entire base sharing the load equally with the course below. This was not merely stacking, it was a precise, iterative dance of trial and refinement. Each perfectly seated stone locked the structure's integrity tighter, turning a growing pile into a unified, gravity-bound whole. The ramp could be dismantled, the pulleys put away. What remained was a testament to that final, silent moment of perfect alignment, where human intention and celestial geometry became one solid, enduring form. Gravity is the silent architect of these ancient wonders. While we marvel at the precision of the cuts and the scale of the stones, the true genius lies in a deceptively simple principle. These structures were designed to let physics do the work. They are monuments to equilibrium, where every stone is a participant in a delicate, permanent balancing act. The key is not just placing a heavy block, but placing it so its own weight becomes an anchor. Each stone is shaped and positioned so its center of gravity, the point where its mass is perfectly balanced, sits securely within its own footprint on the stone below. This prevents any individual piece from tipping or rocking, turning a potential weakness into a source of strength. But gravity alone is not enough to withstand the lateral forces of earthquakes or centuries of settling. This is where geometry becomes the master lock. Look at the walls of Sacsayhuamán. Those polygonal stones are not just fitted together, they are a three-dimensional jigsaw puzzle. Each irregular face and angled side creates immense friction against its neighbors, locking them in place and preventing any sideways shift. It is a stone embrace that grows tighter under pressure. Similarly, the stacked marble drums of a Greek column are not simple cylinders. They were often tapered slightly, and the central wooden dowel acted as a guiding pin, ensuring the immense vertical load was transferred perfectly down the centerline. This interlocking is passive. It requires no maintenance, no glue to renew. It is a system that trusts the stone itself. The builders took this understanding a step further with subtle, intentional imperfections. Greek architects employed intosses, that slight swelling in the middle of their columns. This was not just for visual appeal, it was a structural calculation. The curve helped distribute the load more evenly through the stone and countered the optical illusion of sagging, which in a purely physical sense reinforced the perception and reality of stability. In fortress walls from Peru to Mycenae, we see another technique, batter. This is the intentional inward lean of a wall as it rises. It is a powerful visual statement of solidity, but it is also pure physics. By angling the faces inward, the weight of the upper stones is channeled diagonally down and into the heart of the wall and the ground below, rather than pushing outward. It turns the wall's own mass into a force that consolidates its integrity. This passive reliance on weight and shape has a profound consequence. These structures often grow more stable with time. As the earth shifts minutely and the stones settle under their own colossal weight, they compress together, finding a more perfect, permanent resting place. They adapt. Mortar, by contrast, is an active binder. It can dry, crack, erode from weather, and become the failure point. The ancient approach eliminated that single point of failure entirely. The lesson is elegant and enduring. Sometimes the most sophisticated solution is not to add a complex adhesive, but to perfect the relationship between the pieces themselves. By mastering gravity and geometry, these builders created a dialogue between stone and earth that speaks not in decades, but in millennia. But this mastery of stone and gravity points to a deeper truth. A wall that never cracks and a pyramid that touches the sky were never just feats of engineering. They were conversations with the cosmos. The choice to build without mortar was often a philosophical one, a way to embed a civilization's deepest beliefs into the very bones of their world. The seamless, interlocking stones of an Inca wall were more than earthquake-proof. They were a physical metaphor. In a vast empire stretched across treacherous mountains, the perfect fit of polygonal blocks symbolized the ideal of social harmony. Just as each uniquely shaped stone found its essential place in the greater structure, each province and community had a role in the unified empire, or Tawantinsuyu. The wall demonstrated that strength came not from uniformity, but from diverse parts locked together in mutual support. It was architecture as political philosophy, built to endure as long as the social order it represented. For the Egyptians, the material itself was the message. They built with limestone and granite not just because it was durable, but because it was eternal. In a belief system obsessed with the unchanging afterlife, stone was the antithesis of decay. A mud-brick palace might house the living, but only a mountain of stone was fit for a god-king's eternal spirit. The pyramid's smooth, immutable faces, meeting at a single point piercing the heavens, were a machine for immortality. They were a permanent gateway, a frozen ray of the sun, designed to project the pharaoh's power and divine essence across millennia. The absence of mortar here was a statement of finality and perfection, a tomb built not for centuries but for forever, mirroring the timeless realm it was meant to access. Across the Mediterranean, the Greeks pursued a different kind of permanence, one of ideal form. The Parthenon's marble blocks, fitted with such precision, were the building blocks of an idea. Its proportions obeyed the golden ratio, a mathematical harmony they saw as the underlying principle of a rational universe. The temple was a testament to human reason's ability to perceive and recreate cosmic order. In the context of Athenian democracy, this was a communal ideal. The flawless collaboration of countless stones reflected the ideal of citizens working in harmony for the greater good of the polis. The labor itself, paid for by the public treasury and executed by free citizens and metics, was a civic act. Building it strengthened the body politic as much as the Acropolis rock. This leads us to the human scale of these wonders. The immense labor required, the decades of hauling, carving, and fitting, was never merely economic expenditure. It was often a sacred duty, a form of tax paid in sweat, or a seasonal communal service that bound people together. Participating in raising a pyramid or a temple wall was a shared rite of passage, transforming abstract loyalty into a tangible, muscular memory. When you have pulled a rope to move a stone that will outlive your grandchildren, you are invested. You become part of the story. This collective endeavor ensured these structures were not just imposed by rulers, but were cherished as central pillars of identity. They were maintained, protected, and revered because they literally contained the labor and the spirit of the community. The method of construction, this patient, mortarless locking of stone upon stone, was thus inseparable from the meaning of the building. It turned engineering into a sacred act, a slow, deliberate prayer made physical. The perfect joint was not just a technical achievement, it was a signature of belief, a civilization's way of whispering its values into the ear of eternity. These whispers of eternity were not always grand. Sometimes they were small, quiet, and shaped like a prayer. On the windswept, rain-lashed islands off Ireland's western coast, you will find clusters of strange, rounded structures that seem to grow from the earth itself. These are the Beehive huts or clochons, built by early Christian monks between the 6th and 12th centuries. They are the humblest of the mortarless wonders, and in their simplicity, they reveal a different kind of genius. Here, the goal was not to impress with scale or divine alignment, but to achieve a perfect, self-sufficient shelter using nothing but the flat stones scattered across the ground. The monks who built them had no vast quarries, no armies of laborers, only their own hands, their faith, and an intuitive understanding of how stone could be coaxed into a sheltering dome. They did not use arches or complex geometry. Instead, they mastered a technique called corbeling. Imagine you are stacking a pile of books, but with each new book, you push it a tiny bit further over the edge of the one below. If you do this carefully in a circle, the stack will begin to curve inward. This is the essence of corbeling. The monks would lay a foundation ring of stones on the ground. The next ring will be placed not directly on top, but slightly inward, overhanging the first by an inch or two. They would repeat this process, each concentric ring leaning further inward, until the opening at the top was small enough to be sealed with a single, flat capstone. The result is a perfect dry stone dome. The magic of this method is its beautiful, self-supporting logic. The weight of every stone in the dome creates a continuous compressive force, pushing inward and downward. Each stone is simultaneously held up by the one below it and holding up the one above it, locked in a state of balanced tension. It functions like a three-dimensional arch where the force is distributed evenly throughout the entire shell. There is no weak point, no need for a binding agent. The structure's own mass is its mortar. This made the clochons uniquely suited to their brutal environment. The Atlantic gales that would peel the roof off a thatched hut or find the weakness in a mortared wall simply flow over the smooth, curved surface of the Beehive hut. Rain runs off it like water off a stone, well, because it is a stone. The thick walls provide insulation against the cold and the constant damp. These were places of profound austerity, built by monks seeking solitude and a direct, unadorned connection to their spirituality. The hut was a physical manifestation of that vow, a bare stone cell that offered only the most essential protection from the elements, allowing the inhabitant to focus entirely on contemplation. The clochons show us that the principles of mortarless construction are not exclusive to empires and pharaohs. They are a universal language of stone, adaptable to any scale. With nothing but local materials and a profound, hands-on knowledge of load and counterbalance, these monks built shelters that have endured over 1,000 years of some of the fiercest weather in Europe. They stand today not as ruins, but as intact, silent testaments to a different kind of power, the quiet, resilient strength found in simplicity and perfect balance. The Beehive hut's quiet perfection stands in stark contrast to another mortarless wonder, one born not from solitude but from the clamor of empire. The Romans, masters of the arch and inventors of revolutionary concrete, also understood the timeless strength of stone fitted to stone. Their most enduring legacies often rest upon this ancient principle, woven into the very sinews of their civilization. To supply their sprawling cities with fresh water, they engineered aqueducts, channels that marched across valleys and hills for miles. And while the water channel itself might be lined with concrete, the colossal structures that carried it were frequently feats of dry stone mastery. The Pont du Gard in southern France is a breathtaking example. This three-tiered bridge, part of an aqueduct stretching over 30 miles, was built in the 1st century. Its great arches are not bound by mortar, but by precision and gravity. The Romans quarried local limestone, cutting each block into a perfect wedge shape. These voussoirs, as they are called, were then carefully assembled on a temporary wooden frame, an arch-shaped scaffold known as centering. Each stone leaned on its neighbor, transferring weight sideways along the curve of the arch. But the true magic happened with the final piece, the keystone. This central wedge at the very apex of the arch was the lock. Once it was dropped into place, the entire structure transformed. The weight of the stones and the water channel above was converted into compressive force, pushing outward against the sturdy piers on either side. The keystone received that force from both sides, locking every other stone in a state of perfect, balanced tension. The wooden centering could be removed, and the arch stood freely, a permanent stone rainbow. The precision required for this was extraordinary. If the angles of the voussoirs were even slightly off, the forces would not distribute evenly, and the arch would weaken or collapse. The Romans achieved this with simple but effective tools, plumb lines, levels, and the disciplined skill of their masons. This dry stone construction was a strategic choice. In an aqueduct, constant moisture is the enemy of most mortars, which can erode and wash away. By relying on geometry, the Romans built a system that was essentially maintenance-free. The Pont du Gard did not just stand, it worked, channeling millions of gallons of water every day for centuries, long after the administrative might of Rome had faded from the region. This reflects a core Roman engineering philosophy, pragmatic adaptation. They did not invent the arch or dry stone construction, but they studied and perfected the best techniques from every culture they encountered, scaling them up to an unprecedented level to serve the needs of an urban empire. Their aqueducts were not just feats of engineering, they were the lifeblood of civilization, enabling public baths, fountains, and sanitation that supported dense populations and public health. The quiet endurance of those mortarless arches allowed that legacy of water and the community it fostered to flow long after the empire itself was history. They built not for kings or gods alone, but for the bustling, everyday life of the city, proving that the most resilient infrastructure often relies on the simplest, most ancient truth, a perfect fit. The earth beneath these monuments is rarely still. From the grinding tectonic plates that raise the Andes to the fault lines that snake beneath the Aegean Sea, many of the greatest mortarless structures were built in landscapes that constantly tremble. Their survival is not mere luck, it is evidence of a forgotten science, a deep understanding of seismic design learned through hard experience. These ancient cultures were not just builders, they were master earthquake engineers. Look again at the zigzagging walls of Sacsayhuamán. Those polygonal stones, each a unique shape, are not simply locked together, they are a community of stones. During an earthquake, the ground moves in a sudden, violent jolt. A rigid, mortared wall would try to resist that motion as a single, brittle unit, and it would crack and crumble. But the polygonal masonry behaves differently. Each irregular stone can shift and rock independently, just a tiny amount against its neighbors. This movement absorbs and dissipates the seismic energy, scattering it through the countless friction points between the stones. Once the shaking stops, gravity and their own interlocking shapes guide them to settle back, almost like a self-healing puzzle. Modern engineers have a term for this principle, dynamic isolation, where a structure is designed to move with the ground motion rather than fight it. These ancient builders achieved it with stone alone. They applied this wisdom to every element of design. Walk through the ruins of an Inca city, and you will notice the doors and windows are not perfect rectangles. They are trapezoids, wider at the bottom and narrower at the top. This shape is far more than an aesthetic choice. It is a seismic reinforcement. The angled sides naturally channel the tremendous forces of a quake downward into the massive stone lintel and the sturdy walls on either side, preventing the collapse of the opening. The same logic applies to the inward lean or batter of fortress walls. This subtle angle uses the wall's own immense weight to push it back into the earth during a lateral shock, consolidating its stability. This profound knowledge did not come from a textbook. It was likely earned through painful observation, the collective memory of generations who witnessed what stood and what fell when the ground shook. It was a process of trial and error spanning centuries, where each tremor was a brutal but instructive teacher. The solutions they developed were elegantly passive, requiring no metal reinforcements or complex mechanics, just a brilliant manipulation of mass, geometry, and friction. In an age where we build ever taller and more rigid structures, these ancient monuments offer a humbling lesson in resilience. They teach us that sometimes, to endure the greatest forces, you must learn to yield, to flex, to dance. By designing in harmony with the Earth's power rather than in defiance of it, they created a dialogue with instability itself, and in that conversation, they found a form of permanence that rigid resistance could never achieve. The silent perfection of these stones whispers a question that modern tools cannot easily answer. We picture a mason with a simple hammer and chisel, but that image alone cannot explain surfaces polished to a glassy sheen or cut so straight they seem machined. The basic toolkit is clear, but the full extent of ancient stone working technology remains one of history's most tantalizing mysteries. How did they transform rough, quarried rock into faces so flawlessly flat and smooth? The answer likely lies not in a single magical device, but in a sophisticated, cumulative craft tradition that has left almost no trace of itself behind. We have the finished product, but the workshop secrets of the masters are largely lost. Consider the granite of an Egyptian sarcophagus, a material so hard it ranks just below diamond on the scale of mineral hardness. A copper chisel alone would barely scratch it, so how were its interior and exterior surfaces planed so smooth, and how were the precise, straight channels for the lid cut? Many researchers point to the clever use of abrasives. By using a slurry of water and an even harder granular material, like quartz sand or crushed emery, workers could effectively turn a simple copper saw or a flat piece of stone into a powerful grinding tool. A copper blade, pulled back and forth with the abrasive slurry trapped beneath it, would slowly but relentlessly wear through the granite. The sand does the cutting, the metal merely guides it. For polishing, they could use progressively finer powders, achieving a lustrous finish through patient, repetitive motion. This method is deceptively simple, but its effective use required generations of refined knowledge, knowing which sands worked best, how much pressure to apply, and how to maintain perfect alignment over days or weeks of work. Beyond saws, there is the puzzle of the flat surface. Creating a perfectly level plane across a multi-ton block without modern equipment seems impossible. Yet they did it repeatedly. The likely technique again involves abrasives and a profound understanding of geometry. By using a known flat surface, perhaps a carefully leveled stone slab, and sprinkling abrasive sand between it and the block being worked, masons could grind the high points down through a circular rubbing motion. They would check for flatness with simple yet incredibly accurate tools. A water-filled trench provided a universal horizon. A three-legged frame with a hanging plumb bob could tell them if a surface was perfectly level. Some theorists suggest they may have used early forms of templates or angle gauges made of wood or stone to transfer complex shapes and angles from a master plan onto the raw rock. The straight, parallel lines found on some foundation stones hint at the use of string lines coated in ochre or other pigment, snapped against the stone to leave a perfect guide mark. This leads to the more speculative edge of the mystery. A few carvings and blocks show cuts and drill holes so precise that some have wondered about lost or unconventional methods. Could they have used tubular drills, perhaps of copper with abrasive grit, that allowed for remarkably clean, circular bores? There are even fringe theories about the use of sonic or vibrational tools, though these remain firmly in the realm of speculation without solid archaeological evidence. The more plausible and perhaps more profound truth is that the true tool was not made of copper or stone, but of time and tradition. The real technology was the cumulative, refined knowledge passed from master to apprentice over centuries. It was a living library of technique, knowing exactly how to listen to the ring of a hammer strike to gauge the stone's integrity, or how to exploit natural cleavage planes. This craft tradition was so effective, so optimized, that it left little physical evidence behind. The masters did not need complex machinery. They had a deep, intuitive partnership with their material, built on thousands of years of collective trial, error, and perfected skill. The perfect stone is not a mystery of a lost super tool, but the signature of a lost super culture, one that understood that the most advanced technology is often the knowledge held quietly in human hands. This raw, intimidating power stands in stark contrast to the refined geometry of the Parthenon, just a few miles away in the same landscape. The entrance to the citadel of Mycenae is not a graceful portal, but the gaping maw of the Lion Gate. Above it, two massive stone lions flank a central column, their heads lost to time, standing guard over a threshold built for giants. The walls they crown are the very definition of Cyclopean, a term given by the later classical Greeks who could not fathom how their ancestors moved such stones without the help of mythical, one-eyed giants. Built around 1350 before the Common Era, these fortifications were not about mathematical harmony. They were about one thing: sheer, unbreakable defense. The technique here is a world apart from the meticulous polygonal puzzles of the Inca. Workers quarried enormous, irregular limestone boulders, some weighing many tons. Instead of painstakingly carving them into intricate shapes, they roughly hammered them into more manageable forms, then leveraged their natural contours. The genius was in the selection and placement. A master builder would examine a boulder, see a deep notch on one side, a protruding bulge on another, and intuitively understand how it could lock into the stones already in the wall. They were building a three-dimensional jigsaw puzzle where the pieces were not pre-cut, but chosen and minimally shaped to fit. The gaps between these gigantic blocks were then packed with smaller stones and rubble, not as mortar, but as chocks to prevent any shifting. This created a wall that was not a smooth plane, but a textured, chaotic mosaic of stone, a topography of power. The stability was brute force physics. Each boulder's immense weight and irregular shape created tremendous friction against its neighbors, while the smaller infill stones acted like countless tiny wedges, eliminating any point of weakness. This method was likely born from necessity, a need for rapid, formidable construction in a time of uncertainty and conflict. It speaks to a different kind of engineering intelligence, one based on practical speed and an intimate, almost instinctual, reading of natural form. The wall was not meant to be beautiful in the classical sense. It was meant to be overwhelming, to project an aura of invincibility to any approaching army. To stand before these walls is to feel a palpable sense of intimidation, a message carved not in words but in the very mass of the mountain itself. This Cyclopean style proves the incredible adaptability of Mortarless principles. From the celestial precision of the pyramids to the dynamic interlock of Sacsayhuamán, and now to this rustic, muscular bulwark, the core idea remains: trust the stone. Here, that trust was placed not in perfect seams, but in the raw, balanced power of nature's own shapes, piled high by human will into a statement that has endured not just as architecture, but as myth. The perfect cut of a stone was a secret whispered not in books, but in the rhythm of a hammer. In a world without engineering manuals or digital blueprints, the monumental knowledge required to build these wonders lived and breathed within people. It was a living library, passed from one generation of hands to the next through a Master-Apprentice tradition that was the true backbone of these civilizations. A young boy entering a mason's guild would not start by studying geometry on papyrus. He would begin by feeling the stone. His first lessons were in the quarry, learning to listen for the telltale ring of a healthy seam, to identify the natural cleavage lines where a hammer blow could be most effective. He would spend years performing the brute force tasks, hauling rubble, mixing abrasive sands and rough shaping blocks, his body slowly memorizing the weight and resistance of the material. Only after a decade or more of this foundational labor would he be trusted to work on the finer aspects, the precise dressing and the sacred act of test fitting. This was knowledge earned through calluses and patience, a curriculum written in physical experience, but it was not silent work. The transmission of this complex craft was almost certainly woven into the fabric of culture itself. Rhythmic chants would coordinate the teams hauling a sledge, their beats ensuring a unified pull. Stories and songs likely held practical wisdom in metaphorical form, tales of gods shaping mountains that encoded the best seasons for quarrying when the stone was driest and least likely to fracture. Mnemonic poems could have preserved the ratios for a stable arch or the angles for a self-locking joint. In societies like ancient Egypt, a scribal or priestly class would have guarded the higher mysteries, the precise astronomical alignments, and the sacred mathematics that dictated a pyramid's proportions. They were the keepers of the celestial blueprint, while the master masons were the translators, turning those abstract numbers into tangible, perfect stone. This system was profoundly effective, creating a seamless pipeline of expertise that could sustain projects lasting generations. Yet its strength was also its profound fragility. This knowledge was not stored on a shelf, it was stored in people. When a civilization faced a period of decline, upheaval, or conquest, the chain of transmission could be broken. The master might die before passing on his most nuanced understanding of a specific granite, or the communal song that held the key to a particular foundation ritual might fade from memory. This fragility is likely why the methods behind some structures feel just out of our reach today. We can reverse engineer the what, but the intimate how, the tactile secrets of the craft, vanished with the last apprentice who never became a master. It highlights a timeless truth about human expertise. The deepest forms of knowledge are not merely informational, they are experiential. They reside in the practiced feel of a tool, the intuitive judgment of a seasoned eye, the collective muscle memory of a community. A written instruction can tell you to cut a stone at a 22-degree angle, but it cannot teach your hands the subtle pressure that prevents it from shattering. The silent, enduring stones are therefore a testament to more than engineering. They are monuments to a lost dialogue, the slow, patient conversation between a master's voice and a student's hands, a conversation that once built the world. Long before the first pyramid rose in Egypt, a different kind of celestial machine was taking shape on a green hill in Ireland. The passage tomb of Newgrange, built around 3,200 years before the Common Era, is a silent giant of the Neolithic world. Its massive, circular mound, covered in a gleaming white skin of quartz stones, looks like a natural part of the landscape, but beneath that grassy exterior lies a marvel of dry stone engineering and profound intention. The entire internal structure, a long, narrow passage leading to a cross-shaped central chamber, is built without a single drop of mortar. The walls are formed from enormous, upright stone slabs, while the roof is a breathtaking achievement of corbelling. Here, the builders stacked rings of flat stones, each layer overlapping and leaning inward until they narrowed the space high above the floor. At the peak, a single, immense capstone seals the chamber, creating a perfect, self-supporting stone dome that has kept the interior dry for over 5,000 years. This was not merely a tomb, it was a carefully engineered vessel designed for a specific, luminous moment. Above the entrance, a small, rectangular opening known as a roof box was constructed with the same precise, mortarless technique. And this opening holds the key to the entire structure's purpose. For just a few minutes at dawn on the winter solstice, the shortest day of the year, a narrow beam of sunlight passes directly through this roof box. It travels down the long, dark passageway, growing wider as it goes, until it floods the inner chamber with a golden light, illuminating the intricate spiral carvings on the rear wall. This event was not an accident. It required the builders to possess and apply a sophisticated understanding of astronomy, aligning the entire 60-foot passage with the precise rising point of the sun on that one critical day. The seamless, mortarless construction was essential to this function. Any settling or shifting of the stones over centuries could have misaligned the sacred beam. By relying on the stable, interlocking principles of corbeling and massive slab construction, they created a permanent, unchanging sightline to the heavens. Newgrange stands as a powerful testament to an idea that mortarless building was about far more than durability. It was a method chosen to create a sacred space of perfect cosmological alignment. The stones had to be eternally steadfast because they were the physical anchors for a celestial event, a way to capture the rebirth of the sun itself and bring its life-giving light into the realm of ancestors. In this quiet Irish field, engineering, astronomy, and spirituality were not separate disciplines. They were woven together into a single, enduring stone prayer, a dialogue with the cosmos built to last for millennia. The stones they chose were not accidental. A master builder did not simply pick the nearest rock. He selected a partner for a 1,000-year conversation, reading the landscape with the eye of a geologist and an ecologist. This was a profound material wisdom, a deep understanding that the right stone in the right place was the first secret to longevity. They knew limestone, relatively soft and workable, was perfect for the intricate carving of hieroglyphs and the smooth casing of a pyramid. They reserved granite, brutally hard and nearly impervious to erosion, for the sarcophagi meant to last forever and the obelisks that pierced the sky. Sandstone, with its incredible compressive strength, formed the backbone of temples meant to bear immense loads. This knowledge went beyond simple categories. Quarrymen could read the grain of the stone like the lines on a palm, selecting blocks from specific seams that would weather evenly, resist cracking, or take a fine polish. They were not just extracting rock, they were curating it for a specific destiny in a specific wall, under a specific sun or rain. This intimate partnership with place extended to a principle we now call local sourcing. With staggering exceptions for symbolic stones, most monuments were built from materials found within a few miles, often within sight of the construction site. This was not a limitation, it was a strategic advantage. It minimized the colossal energy required for transport, turning a logistical nightmare into a manageable challenge. But more importantly, it meant the building was made from the bones of its own land. The stone had already endured that specific climate for eons. It was pre-adapted to the humidity, the temperature swings, the very chemistry of the local rain and soil. A structure built from local limestone in Egypt was in dialogue with the desert, while one built from Andean granite was in conversation with the mountain winds. This local harmony created a second, brilliant advantage: breathability. A mortarless wall is not a solid barrier, it is a living membrane. Tiny, intentional gaps and the natural porosity of the stone allow moisture from rain or groundwater to seep in, but more importantly, to evaporate back out. In a mortared wall, water gets trapped behind the impermeable seal, then freezes in cold weather, expands with tremendous force, and slowly spoils the stone face apart from the inside. The ancient method avoided this trap entirely. Their walls could breathe, letting moisture pass through without building up destructive pressure. This understanding of hydrodynamics, of how water moves through and around stone, was key to their resilience. They were building with the environment, not against it. They observed how certain stones darkened with lichen but did not crumble, how others shed water in a particular way. This was not abstract science, it was learned through generations of watching, testing, and remembering what worked. The result was a form of sustainability we are only now fully appreciating. These builders achieved an incredible feat. They created monuments of immense permanence with an astoundingly low environmental footprint, using local materials and processes that required no toxic binders or complex supply chains. Their legacy is a masterclass in true long-term thinking, showing us that endurance is not just about defying time, but about understanding your place within the natural world so completely that your creation becomes a part of its enduring rhythm. But even the most stable foundation must contend with a living, breathing world. In the dense jungles of Cambodia, the air itself is a force, thick with humidity and pulsing with the rhythms of the monsoon. Here, the Khmer Empire raised Angkor Wat, a temple complex of such scale and grace it was meant to mirror the cosmic home of the gods. While its iconic lotus bud towers are assembled from sandstone blocks often joined with a vegetable-based compound, the true secret to its 900-year endurance lies beneath the splendor. The massive platform it rests upon and the great wall that encloses its sacred space are masterworks of dry stone engineering. The Khmer builders chose laterite, a porous, iron-rich stone that hardens upon exposure to air for these foundational elements. They cut these blocks with exacting precision and fitted them together without any binding paste, creating a rigid yet breathable lattice. This was a deliberate calculation. In a climate of relentless heat and drenching seasonal rains, a rigid mortar would be a death sentence. It would trap moisture, then crack and crumble as the stone expanded and contracted with the temperature, a cycle repeated thousands of times over centuries. By relying on precise fitting and gravity, the Khmer engineers allowed their foundation to behave like a living system. The tightly joined stones distributed the immense weight of the temple evenly, while the tiny, intentional gaps between them permitted water to drain and the entire structure to flex minutely with the swelling earth. This hybrid approach reveals a brilliantly pragmatic mind. They understood that different parts of a building faced different challenges. The decorative carvings and soaring towers required a finer, more sculptural joinery for which their organic compound was suitable. But for the elements that interacted directly with the volatile, wet earth, only the timeless principle of interlocking stone would suffice. It was a nuanced application of material science, choosing the right tool for the right job. The dry stone base was not a primitive fallback. It was the sophisticated, essential choice for permanence in a land where the environment itself is in constant, dramatic motion. Angkor Wat does not simply stand in the jungle. It is in a silent, stable dialogue with it, its mortarless foundations patiently absorbing the push and pull of a breathing world so that the dreams carved in sandstone above could touch the sky. That pursuit of the seamless joint reveals a deeper truth about these builders. For them, the invisible seam was more than a technical marvel. It was an artistic and philosophical ideal. The perfect fit represented something pure, a state of unity where no weakness, no flaw could find a home. It was the physical expression of a flawless whole. The Inca spoke of joints so tight that not even air could pass between the stones, a standard that sounds less like a building code and more like a spiritual aspiration. This was not about hiding their work, but about perfecting it to the point of disappearance. The goal was to make many stones behave as one single, continuous mass. When you look at a wall built this way, your eye does not catch on grout lines or uneven gaps. It slides smoothly over an unbroken surface. The structure appears not assembled, but born, as if it were a single piece of the mountain deliberately shaped or a living form that grew from the soil. This aesthetic choice carries immense power. It communicates through absence, through what is not there. There is no need for elaborate carvings or painted decorations to proclaim the builder's skill. The wall itself is the proclamation. The beauty lies entirely in the execution, in the silent, undeniable proof of control over material and form. It transforms construction from a craft into a high art where the primary medium is precision itself. This creates a profound psychological effect. A mortared wall with its visible lines and potential for crumbling paste reminds you it is made of separate parts. A mortarless wall of perfect joints presents itself as a monolith, an immutable fact of the landscape. It speaks of order wrested from chaos, of human will imposing a perfect, harmonious geometry upon the raw randomness of nature. In this way, the building becomes more than a shelter or a temple. it becomes a manifestation of a civilization's core values, order, unity, and the relentless pursuit of an ideal. The achievement is communicated not with a shout of ornament, but with the quiet, overwhelming confidence of a seamless stone face, a silent yet deafening statement of what people are capable of when they aim not for good enough, but for perfect. Scattered across the sun-baked hills of Provence in southern France, you will find clusters of strange, rounded huts that seem to have sprouted from the earth itself. These are the bories, ancient dry stone shelters built by peasant farmers over centuries, from the Bronze Age right up to the 1800s. They are the ultimate expression of vernacular architecture, built not for a pharaoh or an emperor, but by common hands for common needs. Where the great monuments were expressions of divine power or cosmic order, the bories are a quiet testament to human ingenuity in the face of daily life. Farmers clearing their rocky fields of limestone would pile the stones not as waste, but as the raw material for their own homes. With no mortar, no timber for beams, and only the knowledge passed from father to son, they built these beehive-shaped shelters using the same corbelling technique seen in the Irish clochons. Each circular course of flat stones was laid slightly inward over the one below, slowly curving upward until the dome could be closed with a capstone. The result was a cool, dark space that required no internal supports, creating a surprisingly spacious and sturdy room from nothing but the stones underfoot. This was construction stripped to its purest form, a direct response to necessity. A borie was not a permanent home, but a seasonal shelter, a place for storing tools, sheltering animals, or providing refuge during the long, hot days of the harvest. The skill to build one was not guarded by priests or scribes. It was a practical, everyday knowledge embedded in the rhythm of rural life. Every farmer was, in a sense, an engineer. He knew how to select the flattest stones for the roof, how to angle each course to shed the rare but torrential Provençal rain, and how to shape the entrance to block the fierce Mistral wind. This represents a profound democratization of the mortarless principle. The same understanding of gravity, compression, and geometry that raised pyramids was here applied to building a simple sheepfold. The endurance of the bories is a different kind of marvel. Many stand in silent clusters, their roofs intact, centuries after the families who built them have moved on. They were never maintained, never repaired, yet they persist. Their strength comes from that perfect, self-locking corbelled dome, which settles more firmly into itself with each passing year. They demonstrate that the most resilient structures are often those built in perfect harmony with their immediate environment, using local materials to solve local problems. The bories are not ruins, they are still functional artifacts of a practical wisdom so deeply ingrained it became instinct. They remind us that the greatest architectural lessons are not always written in grand temples, but sometimes in the quiet, enduring logic of a stacked stone wall, built by someone who simply needed a place out of the sun. The seamless stone before our eyes is a beautiful lie. Its perfection is not the product of random chance or brute force, but the final, physical answer to a complex mathematical equation. Behind every silent, interlocking joint lies a hidden world of advanced geometry, a language of angles and ratios that these ancient builders spoke fluently, long before such concepts had formal names in textbooks. This was the true, invisible mortar that held their worlds together. The Egyptians did not simply decide a pyramid should be steep, they calculated its form with a unit called the seek. This was a specific ratio, a consistent slope that defined how many horizontal units a face would recede for each single vertical unit it rose. Maintaining this exact seeked across millions of blocks over a base spanning 13 acres required a staggering level of mathematical control and on-site surveying. It transformed an abstract angle into a national building standard, ensuring the structure's iconic, stable form. across the Mediterranean, the Greeks pursued a different kind of mathematical harmony. The Parthenon's serene beauty is governed by the golden ratio, a proportion found throughout nature, from seashell spirals to the arrangement of leaves. Its architects wove this ratio into the very fabric of the temple, dictating the relationship between its width and height, the spacing of its columns, even the dimensions of its inner chamber. This was not decorative whimsy, it was a belief that mathematical truth was the foundation of aesthetic and cosmic order. To make these perfect lines appear correct to the human eye, they employed intosses, that subtle swelling of the columns. This curve itself was not random, it followed a precise, complex formula to counteract optical illusion, proving their geometry accounted for both the physical and the perceptual world. But how did a civilization without paper or a written number system like the Inca manage such feats of engineering? While they left no blueprints, they possessed a brilliant tool for logistics, the quipu, a system of knotted cords that could record vast amounts of numerical data, from census counts to resource inventories. This base 10 system likely helped orchestrate the movement of thousands of workers and tons of material. On the building site, their mastery of geometry was hands-on and profound. The perfect squaring of a multi-ton granite block, ensuring each face was a flawless plane meeting at perfect right angles, hints at a practical knowledge of principles we attribute to Pythagoras. They may have used the simple, foolproof 3-4-5 triangle rule, by measuring 3 units along one edge, 4 along another, and confirming the diagonal between those points was exactly 5 units. A builder could guarantee a perfect 90-degree corner every single time. This practical geometry was the silent partner to the mason's hammer. It allowed them to translate vision into reality, ensuring that blocks destined to be separated by quarrying and transport would still fit together with hair-width precision miles away and years later. This intellectual foundation achieved 3 critical things. First, it guaranteed structural integrity, distributing colossal forces along predetermined, stable paths. Second, it created an undeniable visual harmony, a sense of rightness that resonates even with viewers who know nothing of the math behind it. And third, it enabled breathtaking astronomical alignments, like the solstice beam at Newgrange or the cardinal orientation of the pyramids, turning architecture into a cosmic clock. When we stand before these monuments today, we are not just looking at old rocks. We are witnessing the physical incarnation of a civilization's deepest intellectual pursuits. The perfect joint is where abstract thought became permanent form, where a society's understanding of numbers, space, and the heavens was literally set in stone. It reveals that these were never merely projects of manual labor, but triumphs of the mind, a seamless blend of science and art engineered to endure the ultimate test, time itself. Yet this global language of stone found a distinct and elegant dialect in the misty landscapes of feudal Japan. Here, the pursuit of impervious defense merged with a profound respect for natural forces, giving rise to the silent giants of Heimji Castle and its peers. Their power does not roar from towering spires, but whispers from the ground up, from immense stone foundations built entirely without binding paste. This is the art of Ranseki Shiki, the stacked stone style, a masterpiece of mortarless engineering designed to make a castle's very bones earthquake-proof and siege-resistant. At first glance, these bases appear as simple, sloping stone walls, but their gentle, inward curving profile, known as a batter, is a calculated feat of physics. This curve does more than just look imposing. It channels the immense weight of the wooden towers above down and into the heart of the wall, creating a low center of gravity that defies toppling. Each stone in this sloping canvas was chosen with a sculptor's eye. Quarrymen would select granite or andesite boulders, then craftsmen would shape only one face, the outward surface that would be seen. They hammered this face to a remarkably smooth, flat plane, ensuring it would fit tightly against its neighbors. The other sides of the block, the parts that would face the interior of the wall, were left rough and unfinished. This was not carelessness, it was brilliant efficiency. The smooth face created the castle's formidable public image, a seamless, daunting barrier. The rough back, however, served a vital purpose. It gripped the chaotic fill behind it with far greater strength than a polished surface ever could. For behind this elegant stone skin, the wall was not solid rock. It was a carefully engineered composite. Builders packed the interior with a mix of smaller rubble stones and compacted earth. This fill acted as a shock absorber, dispersing the energy of impacts or tremors throughout the entire mass. But the true genius of Ranseki Shiki lies in its hidden stitches. To bind the beautiful outer skin to the rugged inner core, masons used special stones called ejimaki ishi or tie stones. These were long, rectangular blocks, sometimes stretching several feet back into the wall. They were placed at strategic intervals with their narrow end forming part of the visible face, while their long body penetrated deep into the rubble fill, locking the entire structure together like a stone pin. This created a monolithic strength where the outer veneer could not simply peel away under assault. The precision required was immense. Every visible stone had to be cut to fit its unique position on the sloping curve, and the placement of each tie stone had to be perfectly calculated. The result was a fortress that could withstand the dual terrors of feudal Japan, human conflict, and the restless earth. During a siege, the sloping wall caused projectiles from catapults or guns to deflect upward, robbing them of their full force. More importantly, during an earthquake, the entire structure was designed to move as one flexible unit. The mortarless joints allowed for minute shifting. The rubble core absorbed and dissipated the energy, and the low, sloping profile resisted collapse. It was a system that embraced motion to achieve stability, a philosophy deeply aligned with the natural world. This Japanese technique stands as a powerful Eastern parallel to the dry stone wonders of the West. Developed in complete isolation from the Incas or the Mycenaeans, it arrived at remarkably similar solutions: the use of batter, the strategic filling, the reliance on gravity and friction. It reveals a profound truth about human ingenuity. When faced with universal challenges like defense and seismic survival, brilliant minds across the globe often converge on the same elegant principles. The stone base of Heimji Castle is more than a foundation. It is a quiet manifesto in rock, declaring that true resilience is not about rigid defiance, but about intelligent, flexible integration with the forces you cannot control. The silent conversation between ancient stones is no longer a forgotten language. In a world confronting climate change and seismic risk, the timeless principles of mortarless construction are speaking with renewed urgency. Architects and engineers searching for sustainable and resilient ways to build are looking back to these ancient methods not as curiosities, but as sophisticated, proven solutions. This is not about romanticizing the past. It is about recognizing a profound, enduring intelligence that our modern world desperately needs to remember. The most direct link to this legacy is found in the revival of a living craft. Dry stone walling, once a common rural skill, is now a formally recognized art form with guilds and societies across Europe and North America dedicated to its preservation and teaching. These modern wallers use no mortar, no concrete, just the same principles of selection, placement, and gravity that built the foundations of Heimji Castle or the pastoral bories of Provence. Their work, seen in landscape restoration and new construction, proves the technique is not obsolete. It is actively beneficial, creating beautiful, permeable barriers that support local ecosystems and last for generations without any carbon-intensive binder. On a larger, more analytical scale, the seismic secrets of structures like Sacsayhuamán are being unlocked with modern technology. Engineers now use three-dimensional laser scanning to map the intricate joints of polygonal masonry with millimeter accuracy. This data reveals patterns of interlocking and weight distribution that are informing the design of contemporary earthquake-resistant buildings. The ancient idea of allowing a structure to flex and dissipate energy rather than rigidly resist it is a leading principle in modern seismic design, showing that the Inca were masters of dynamic isolation long before the term existed. This philosophy extends into the heart of the green building movement. A core tenet of sustainable architecture today is called design for disassembly, the idea that buildings should be constructed so their materials can be easily separated and reused at the end of their life. This is the inherent, elegant logic of dry stone construction in its purest form. A mortarless wall is, by its very nature, designed for disassembly. Every stone can be taken down and rebuilt elsewhere or returned to the landscape, leaving no toxic residue. It is the ultimate circular economy, a zero-waste system perfected millennia ago. Our appreciation for this ancient genius is being deepened by digital eyes. Advanced scanning allows researchers to see things the naked eye cannot, revealing tool marks, subtle wear patterns, and the breathtaking micro-precision of joints we once thought were simply smooth. This technology is not demystifying the monuments, it is enriching our wonder, showing us that the craftsmanship was even more refined than we imagined. The legacy of these builders is therefore not locked in the past. It is a vibrant, living source of inspiration, a demonstration that true innovation often means rediscovering fundamental truths. In their patient, precise work, we find answers to our most pressing modern questions: how to build structures that can withstand a changing planet, how to create without poisoning the earth, and how to forge a built environment that feels not imposed, but intrinsically connected to the human hand and the natural world. The ancient stones were a dialogue with eternity, and now, finally, we are learning how to listen. Even with all our modern tools, the stones still hold their secrets tight. We can map their surfaces with lasers and peer beneath them with radar, yet fundamental questions about their construction remain open, active debates that keep the past vibrantly alive. Take the Great Circle of Stonehenge on the English plain. We understand how the massive Sarsen stones might have been transported, and even how the uprights were set into their sockets. But the true head-scratcher is the lintels, those colossal horizontal stones perched nearly 20 feet in the air. How did a society without pulleys or cranes lift these multi-ton capstones and then slot them precisely into the carved grooves on top of the uprights? The most plausible theories involve elaborate systems of timber platforms, levers, and earthen ramps, a kind of slow-motion ballet of wooden scaffolding and coordinated manpower. Yet the exact sequence, the specific engineering choreography, remains a puzzle that each new researcher tries to solve. This is not just about one monument, it is about understanding the limits and ingenuity of Neolithic problem-solving. Inside the Great Pyramid, another mystery unfolds in the dark. While the broad strokes of its construction are known, the precise order and method for building the intricate inner chambers, like the King's Chamber with its gigantic granite beams, is still debated. Were these rooms built as the pyramid rose around them, or were they constructed within a pre-existing mass of stone? Each theory demands a different vision of the project's timeline and on-site logistics, a different story of ancient project management. These questions lead to even more speculative frontiers. A handful of controversial theories, often on the fringes of mainstream archaeology, suggest that some cultures might have possessed a lost knowledge of materials, using plant-based chemicals or focused heat to temporarily soften granite or andesite, making it easier to shape. While most evidence strongly supports the patient use of abrasives and precise hammering, the very existence of these debates highlights a powerful truth. We are still uncomfortable with how much skill and time the ancients truly possessed. Their patience itself is a technology we have lost. Beyond the physical, how lies the profound social question of who and why? For generations, the narrative was dominated by images of conscripted labor, of vast populations driven by the whip to build for a tyrant. This view is now largely overturned by archaeological evidence. At Giza, workers' tombs discovered nearby suggest they were fed high-quality meat and fish, received medical care, and were buried with honor near the monument they helped build. This points not to slavery, but to a rotating national service, a duty performed by skilled artisans and farmers during the Nile's flood season when fields were underwater. They were likely revered for their role in a sacred national project. Similarly, the Inca mitre system was a form of labor tax, but one embedded in a reciprocal social contract where the state provided sustenance and security. The work was arduous beyond our comprehension, but it was often framed as a communal, even spiritual obligation. Decoding this social organization is crucial because it changes the very meaning of the monuments. Were they symbols of oppressive power or of collective identity and shared belief? The answer shapes how we hear the story these stones tell. This is why the field of archaeological engineering is so dynamic. It is a detective story where the crime scene is millennia old. New technologies act as our magnifying glass. Ground-penetrating radar reveals hidden chambers and voids without lifting a single stone. LiDAR scans strip away jungle canopy to expose forgotten city grids. Researchers are now applying artificial intelligence to analyze patterns in stone cutting or the wear on ancient tools, searching for digital fingerprints of individual workshops or standardized techniques. Each scan, each algorithm offers a new clue. The enduring mysteries ensure these structures are never just static relics in a textbook. They are active puzzles, constantly inviting us to look closer, to question our assumptions, and to humbly acknowledge that the past still has much to teach us about ingenuity, cooperation, and the sheer will to make a mark on the world that time itself would struggle to erase. These silent stones ask a question that echoes far beyond engineering. In a world where everything eventually returns to dust, why would a society commit generations to building something meant to defy that very cycle? The answer lies not in the physics of the stone, but in the philosophy of the people who shaped it. For these ancient cultures, constructing a monument to last forever was a profound act of faith, a declaration that some things, memory, identity, a connection to the divine must transcend the fleeting span of a single human life. They were not just building walls, they were building a bridge across the chasm of time itself. The choice of mortarless construction was the physical manifestation of this deep yearning for permanence. It was the most durable, the most eternal method they could conceive. Where a mud-brick palace spoke of the temporary needs of the living, a pyramid of seamless stone spoke to the eternal realm of gods and ancestors. It was a statement carved directly into the landscape, declaring, "We were here, our beliefs mattered, and our presence will not be forgotten." This drive was often a dialogue with the cosmos. Aligning a temple to the solstice sun or shaping a tomb to mirror the stars was a way to anchor human existence within the unchanging rhythms of the universe. The building became a fixed point in a turning world, a testament to a cosmic order that humanity could both perceive and participate in through stone. In this context, the immense labor was never a burden but a sacred investment. The decades of effort were a collective down payment on eternity, a way for every individual who held a rope or dressed a block to contribute to something that would outlive them all, weaving their brief lives into a grand, enduring story. Today, we live in a different kind of world, one often characterized by the opposite principle, planned obsolescence. Our buildings are frequently designed for a lifespan of decades, not millennia. Our products are made to be replaced, not repaired. We build with speed and efficiency, materials chosen for cost and convenience rather than endurance. When we stand before these ancient, silent witnesses, their sheer persistence forces a moment of reflection. They challenge our modern assumptions about value and legacy. What does it mean to build for a future you will never see? What do we value enough today to invest the kind of care, precision, and patience that speaks across 50 centuries? The stones do not judge, they simply endure, offering a quiet mirror to our own civilization. They ask us to consider what, from our bustling, digital age, will remain 1,000 years from now. Not the ephemeral data or the disposable goods, but the physical markers of what we held sacred, what we believed was worth making permanent. In their patient, perfect joints, we see a different relationship with time, one not of frantic speed, but of deliberate, thoughtful slowness. They remind us that permanence is not an accident, it is a choice, a commitment etched not in words, but in the very way one stone is laid upon another. That philosophical choice for permanence took on different shapes across the globe. A fascinating divergence emerges when we compare the mortarless traditions of East and West, revealing how deeply a civilization's worldview is etched into its very walls. While the goal of timeless durability was universal, the paths taken were as distinct as the cultures themselves. In the Western tradition, exemplified by the Greeks and Romans, we see a pursuit of ideal geometry. Their architecture speaks a language of straight lines, perfect right angles, and modular, often rectangular blocks. This was not merely a practical choice, it was a philosophical one. It reflected a core belief in a cosmos governed by rational, mathematical order, a universe that could be understood, measured, and replicated by human reason. The Parthenon is a theorem in marble, its proportions obeying strict ratios. Roman aqueducts march across valleys with a relentless, linear logic. Even their hidden reinforcements, the iron clamps sealed in lead, were a form of controlled, human-imposed order, a technological intervention to perfect nature's stone. The aesthetic was one of clarity, symmetry, and an almost intellectual beauty, where the hand of the architect was meant to be seen in the flawless execution of a preconceived plan. Journey to the east, and the architectural language changes entirely. Look at the polygonal walls of Sacsayhuamán or the sloping stone bases of Japanese castles. Here, the philosophy was not about imposing a perfect geometry onto the rock, but about discovering the geometry within it. Builders worked with the natural, irregular shape of each boulder, meticulously carving it to interlock with its uniquely shaped neighbors. This was an architecture of adaptation, not imposition. It reflected a worldview centered on harmony with nature, on fitting into the existing world rather than reshaping it to an abstract ideal. The Japanese concept of ransaki shiki, with its carefully shaped face and rough, gripping back, embodies this duality, presenting a refined face to the world while anchoring itself intimately to the chaotic earth behind it. In the East, the reinforcement was not a hidden metal clamp, but the relentless, patient force of gravity and the brilliant friction of interlocking forms. The structure's strength emerged from the relationship between the stones themselves, a system that was organic, self-regulating, and deeply resilient. This stark contrast in approach leads us to a profound realization. Both traditions achieved the same astounding result: monuments that have defied centuries and earthquakes. This demonstrates a crucial truth about human ingenuity. Technological excellence is not a single, linear path. It is a branching tree shaped by the soil of culture, philosophy, and environment. The Western mind, seeking cosmic order, perfected the straight line and the arch. The Eastern mind, seeking natural harmony, perfected the polygon and the sloping curve. They started from different questions, the Greeks asking, how do we build a perfect form? The Inca asking, how do we make this stone work with its neighbor? Yet they converged on the same brilliant answer, that true strength lies in the perfect fit. This comparative view enriches our understanding immensely. It shows that innovation is culturally framed. A society's deepest beliefs about the universe, its relationship to nature, and the very nature of beauty become the invisible blueprints for its most enduring works. The silent stones of the Acropolis and the Andes are not just feats of engineering. They are crystallized thought, offering us two distinct, yet equally valid conversations with eternity. One speaks in the clear, confident voice of geometry, the other in the adaptive, resilient whisper of the earth itself. From the desert sands of Egypt to the mountain peaks of Peru, these silent structures ask us to reconsider what we mean by progress. Our journey has taken us through the world of the perfect cut, where stones were shaped with a patience we can scarcely comprehend. We have traced the paths of giants, moved across impossible distances by nothing more than ropes, ramps, and human will. We have stood before walls that dance with earthquakes, learning that resilience is found not in rigid defiance, but in intelligent, flexible harmony with the forces of nature. These monuments were never just piles of rock. They were libraries of belief, built by cultures that saw engineering as an act of devotion, a way to embed their deepest values into the very bones of the earth. They chose permanence. They spoke to the cosmos with their alignments and mirrored the social order in their interlocking stones. The knowledge they held was a living thing, passed from hand to hand and generation to generation. A craft so refined it has left us mysteries we are still piecing together today. And perhaps that is their most urgent lesson for our time. In an age of planned obsolescence and disposable materials, these ancient builders offer a masterclass in true sustainability. They built with what was local, in harmony with their climate, creating structures that could breathe, flex, and endure for millennia without a single toxic byproduct. They understood design for disassembly long before it was a modern ideal, constructing walls that could be taken down and rebuilt, leaving no scar on the land. As we face the monumental challenges of our own era, from climate instability to seismic risk, their wisdom speaks with a new clarity. The greatest mystery they leave us with may not be the technical how, but the philosophical why. Why did they commit generations to a project they would never see finished? What did they value so deeply that it was worth such an immense investment of care, skill, and time? Their answer, written in stone, is a challenge to our own values. They remind us that building something lasting is not about the materials alone, but about the intention behind them. It is a choice to think beyond the self, beyond a single lifetime, and to contribute to a story larger than our own. These mortarless wonders are not relics of a forgotten past. They are active conversations with the future, asking us what we will build that is worthy of the centuries to come. Let them inspire you to see the world and our fleeting place within it with a deeper perspective. Look at the walls around you, the bridges you cross, the homes you inhabit, and ask what story they will tell long after we are gone. If this exploration of timeless ingenuity has resonated with you, please consider subscribing for more journeys into the profound mysteries of our shared human story. We would love to hear which of these enduring monuments speaks to you most powerfully, so share your thoughts in the comments below.